Hey everyone, it's Miss Besega, and today is a weekend review. I'm looking to give you a little perspective on what I would like you to know about nuclear physics by the end of this unit. So, a thing that people misunderstand about nuclear physics is that it leads to bombs, it leads to explosions, it leads to bad things, but we feel like if you understand the basics behind nuclear physics, that you'll be able to better make decisions for yourself in terms of health and safety, as well as better understand common current events. So, first off, when we say nuclear physics, what we're referring to is the physics of the nucleus. And inside the nucleus of an atom, there are two types of particles that we call nucleons. There are protons, who are positively charged. I'm going to draw those as red. And let's say I drew, I don't know, 4 protons, red, and 3 neutrons, black. Well, this would make the element with 4 protons and 7 total nucleons. I want to say 4 is beryllium, Be. The number on the bottom of this refers to the number of protons. The number on top is the total number of nucleons. That's neutrons plus protons. And in this case, 3 black neutrons plus 4 red protons equals 7 nucleons total. The total number of nucleons is also called A, the mass number, whereas the total number of protons is sometimes called Z, the charge number. But the nucleus itself is very, very small, and assuming that this is a neutral atom, there would also on the outside, somewhere in this big electron cloud out here, and this is actually a 2-layered electron cloud, would have somewhere floating around here 4 electrons. Right? Actually, maybe one of these electrons should be a little bit closer. Right? So it's neutral because 4 electrons, 4 protons, and the atom itself has the same number of positive and negative charges. Okay, but this would not necessarily be a stable atom. Stability generally occurs when you have an even number of protons and an even number of neutrons, but this is 4, even number of protons, 3, not an even number of neutrons. This is probably an unstable isotope or nuclide of beryllium. And nuclear instability is not the same as chemical instability. Chemical instability comes from the electrons that are on the outside doing the bonding, forming compounds, and things like that. But the nucleus itself can be unstable. Depending on what type of unstable it is, creates 3 ways of dealing with that instability. So, an unstable nucleus could emit an alpha particle. And an alpha particle is a particle that's made up of 2 protons, which I'll draw as red, plus 2 neutrons. Right? An alpha particle has a symbol of alpha for 2. And that's emitted when your nucleus is just too darn big. So a good example of this would be uranium-238. It has too many nucleons, 238 nucleons, so it emits 4 of them. And you could write that as an alpha or an He. And obeying conservation of charge, this transmutates to a different element, thorium. And by conservation of mass, this must be 230, 234. That's an alpha particle. Betas come in positive or negative, and I'm going to draw them blue for an electron. We'll make a beta plus first, would be +1, 0, with a mass of an electron and the charge of a proton, or a 0 minus 1 beta. And this can occur when there's either too many protons or too many too many protons or too many neutrons, respectively. So they still need to obey conservation of mass and conservation of charge. Let's just do one of those since you know they have to obey the same. Carbon-14 is a beta minus emitter. So that means a beta particle is emitted, and that turns one of the neutrons into a proton, making this 14,7 nitrogen. And remember, there is like this extra antiparticle emitted here, but since we generally don't interact with matter, we're going to ignore them. Okay? Finally, a gamma ray, which I'm going to draw as a wave. The reason I'm going to draw this as a wave is that think of it as violet light, but even more energy. It has no mass, it has no charge, and so something that is a gamma emitter, like cobalt-60, and I don't remember cobalt's atomic number off the top of my head, but that's okay. Because it would go from an excited state, indicated with a little tiny star, to the ground state of cobalt-60 with no other particles. That additional energy from going from the unstable to the stable state is emitted as a very super highly energetic light. Now, what we worked on Thursday and Friday then was how these items decay over time. Some things, like carbon-14, have a half-life in the thousands of years. But other things, like uranium, have half-lives of billions of years. Guys, there's a lot of fear about uranium because you know that's the same element that's used in both atomic weapons and nuclear fission, like in power plants. But guys, this doesn't have a super high activity. What I mean by that is uranium has a half-life of 4.5 billion years. That means even though there's a whole bunch of it naturally on the inside of the Earth, it's not decaying so quickly that it's going to irradiate all of us. In fact, if it had a much shorter half-life, then it wouldn't exist on the planet anymore. It would have irradiated away already. The only reason we still have uranium on the planet is of that long half-life. Okay? So, what we were working on Thursday and Friday then was now we know what the nucleus is made of and we know how it becomes more stable. We started talking about the rate of decay. And we came up with this term of half-life. Half-life, and its symbol is T with a little 1/2 next to it, is the amount of time needed for half the cycle or half the amount of the sample to decay away. So if I started with 1,000 particles, the amount of time needed to decay half of a sample. If I started with 1,000 particles, how much time until 500 would be left? And how we could use half-life is we could, use the related rates equation. And in my people that are in Algebra 2A, if you were using this guy in class, where the amount of sample at the end is equal to your original times a decaying exponential, you could totally do that. Similarly, you could do, math peoples, you could do the original amount times 1/2 to the number of half-lives that have passed, t divided by t 1/2. Do that. But you know what, guys? We're only going to be doing this in whole numbers of half-lives. So let me give you an example problem here. Let's say I have, at the start of time, at time 0, I have a sample that has, 6,400 atoms to start, right? And I want to know how long until there's only, actually, how about this? We'll reword it. With a half-life of 8 days, how much is left after 32 days? Oh, man. Got this. Okay. So if the half-life is 8 days, we'll put that in red. 1 half-life passed. That means my sample has to decrease by half. For every number of half-lives that passed, your sample gets cut in half. All right, so at 16 days, there would be, math in my head. Oh, that's a little rough. 1,600 left. That sounds right. After 24 days, there would be 800 left. After 32 days, there would be 400 particles remaining in my sample. You could, if you were in math class and you wanted to use that equation, totally use that if you would like. If not, we would give you some whole number of half-lives that passed. In this case, if a half-life is 8 days, 32 days later means it cuts in half 4 times. 1, 2, 3, 4. Finally, what we'll work on next week is how we stay safe. We'll work on what's called dosimetry. And some things about like what happens with biological tissue when it is exposed to radiation and how we can avoid those sorts of complications. So that being said, that is nuclear physics in a nutshell. Hopefully that review helped a little tiny bit with the material you went over this week. Best of luck to you, and I will see you on Tuesday. Have a great weekend, guys. Bye.